In an effort to improve safety, technology has helped pilots by allowing the development of vision-extending tools, such as weather radar, wind shear radar, TCAS, and other advanced avionics systems. The subject of this video, weather radar, is just that, a pilot's tool, an extended set of eyes that can let you, the pilot, see hazardous weather conditions long before you encounter them. The purpose of this video is to instruct pilots in the operation of the RDR 2000 and RDR 2100 series airborne weather radar systems. It is meant to complement the more in-depth operational information found in the appropriate Systems Pilot's Guide. In this program, we will provide you with the following information: a basic understanding of radar operation, a description of how to use weather radar to detect and avoid dangerous weather cells, a set of suggested guidelines for using a weather radar throughout a typical flight. While the RDR 2000 and RDR 2100 systems are similar, they do have significant differences in capabilities. It is important that pilots know these differences. Again, before operating either system, familiarize yourself with the procedures printed in the pilot's operating handbook. In particular, system differences pilots need to be aware of are: the RDR 2100 features automatic range limiting (ARL) capability. The RDR 2000 does not. The RDR 2100 features auto tilt capability. The RDR 2000 does not. The RDR 2100 operates with a scan of 120 degrees. The RDR 2000 operates with a 100-degree scan. The RDR 2100 operates at a maximum power output level of 6 kilowatts. The RDR 2000 operates with a maximum power level of 4 kilowatts. The word radar is an acronym for Radio Detection and Ranging, or, in other words, locating targets by means of radio waves. The receiver-transmitter unit of a radar generates pulses of microwave energy which are sent to its antenna. At the antenna, these pulses of energy are focused into a beam. The beam is similar to that of a flashlight's beam. When these pulses of energy strike an object, some of the pulsed energy will be reflected back to the radar. The amount of energy which is reflected back to the radar is dependent upon the target's material and its surface orientation. Some objects are much better radar reflectors than others. A raindrop is basically spherical in shape and is a fairly good radar reflector. Snowflakes and dry hail, on the other hand, have very complex structures and do not favor radar reflection. Upon returning to the antenna, the reflected radar signals, or echoes, are displayed in the cockpit on the Plan Position Indicator, the PPI. The radar display presentation appears as a down view of the target being scanned by the radar's beam, unless the pilot has selected the vertical profile function, which displays a vertical cross-section of the weather. The pulse of energy which is transmitted from the radar antenna is in the form of electromagnetic microwave energy. Its frequency of operation is 9.3 billion cycles per second. It travels through space at the speed of light. The distance to a target is determined by measuring the round-trip travel time of the pulse. The direction to the target is the direction the antenna is pointing when it receives the target's echo. RDR 2000-2100 series airborne weather radar installations contain three basic components: an antenna receiver transmitter unit for transmitting, receiving, and processing the radar energy, the antenna which focuses the microwave energy into a beam and continuously scans it from side to side and has the ability to point it at a specific elevation angle, a radome which is a protective covering for the antenna that allows the pulses of microwave energy to pass through it, and a display unit which displays the processed radar echoes as well as providing a mounting point for the system controls. In order for you to properly operate a weather radar, it is essential that you have an understanding of the characteristics of a radar beam. The radar beam searches a horizontal slice of airspace 50 to 60 degrees to each side of the aircraft's longitudinal axis. The size of the antenna is the main factor in determining the width, in degrees, of the radar's radiated beam. The larger the antenna, the smaller the beam width. And more importantly, the smaller the beam width, the more accurately the system can display weather returns, especially at longer ranges. The type of antenna normally used by business and general aviation aircraft is round in shape, with a 10-inch or 12-inch diameter. It produces a cone-shaped beam 8 or 10 degrees wide. Probably the most important aspect of a weather radar is the antenna beam illumination characteristic. To make a proper interpretation of what you are seeing on the display, you must have an understanding of what the radar beam is seeing. Here is a side view of the radar beam characteristic, with a storm depicted at a distance that causes the size of the storm to just fill the 3 dB beam width. This would be the typical situation for a storm at approximately 40 nautical miles with a 12-inch diameter antenna. To enhance your understanding of this tape, it is important to understand and be able to visualize this situation. To help you do this, some observations are in order. Note that the antenna gain versus angle characteristics is a continuous function at all angles. Now, this means there is a gain value associated with all forward angles relative to the selected tilt angle. In this figure, the tilt angle is shown as 0 degrees. This means the beam center is along the same angle as the aircraft's flight angle. Next, the points on either side of the beam where the antenna gain is down 3 dB relative to the maximum gain defines the 3 dB beam width. The remainder of the tape uses the cone-shaped 3 dB beam width extensively to illustrate how the beam spreads with distance. It is also important to realize that the antenna gain does not go to 0 outside the 3 dB beam width. It just continues to reduce with increasing angles. This is what is meant by a continuous gain function. This understanding is important when we discuss ground clutter reflections later in the tape. Also note that there are small lobes of the gain characteristics at fairly large angles. These are called side lobes. Generally, these are not important since the gain value of these lobes is down 25 or more dB from the peak. However, a bad radome can increase these side lobes to a point that they can cause a constant radar reflection from the ground. This is commonly referred to as an altitude ring, because the display will show a concentric ring at a distance equal to the slant range of the side lobe to the ground. Because the radar beam is just like a flashlight's beam, the radar beam's diameter enlarges as it travels outward into space away from the antenna. For those of you who are mathematically inclined, the beam width diameter can be calculated at a given range using the following equation. Beam width in feet equals the range in nautical miles times the beam width in degrees times 100. As an example, if the range is 10 nautical miles and the beam width is 8 degrees, the beam is 8,000 feet wide. Beam width in feet equals 10 times 8 times 100, which equals 8,000 feet wide. At 20 miles, it's 16,000 feet wide. While this is good background information, proper use of a weather radar requires no calculations at all. One of the effects of beam spreading is to reduce the radar's target resolution capability. That is, its ability to separate two targets at the same range but located at slightly different viewing angles. When the distance between two targets at the same range is less than the diameter of the beam, the two targets merge together on the display and appear as one. As the aircraft approaches the targets and its beam diameter at their location becomes smaller than the distance between them, they are resolved as two separate targets. A stabilized antenna means that the antenna continues to scan horizontally relative to the horizon during moderate aircraft maneuvers. To accomplish this, a reference is established by the aircraft's vertical gyro, usually a component of the autopilot or integrated flight control system. With the tilt control set to 0 degrees, the radar beam center is set at the aircraft's altitude and projects 4 degrees above and below the horizontal plane. The tilt control can be used to direct the beam plus and minus 15 degrees with respect to the horizontal plane for a 12-inch antenna. Without stabilization, the antenna tilt angle is referenced to the longitudinal axis of the aircraft and will not be corrected by the gyro inputs during aircraft maneuvers. During maneuvers, heavy ground returns will normally be displayed. Antenna stabilization loses its effectiveness when the combined pitch, roll, and tilt angles exceed about 30 degrees. These limits can be exceeded during high pitch and roll maneuvers and will cause heavy ground returns to be observed on the display unit. Pilots who fly aircraft using conventional vertical gyros can be expected to experience some stabilization degradation during periods of acceleration. This phenomenon is due to precession errors developed within the gyro. These precession errors are caused by aircraft acceleration during takeoff and shallow bank turns of less than 7 degrees. To verify the accuracy of the radar's stabilization system, an in-flight check may be initiated. Fly the aircraft level at 10,000 feet AGL. Select the map mode, stabilization off, and set the indicator at 20 nautical miles. With the RDR 2100, disable the auto tilt by pressing the Tilt Select knob. Set manual gain to maximum. While flying level, which is 0 degree pitch, 0 degree roll, adjust the tilt control until a pattern like this appears. Note, record the tilt position for future reference. If the inner ring of the displayed image is not parallel to the range marks, the mounting of the antenna is not parallel to the horizontal axis of the aircraft. Now, turn the stabilization on. If the display pattern appears as either of these images, the RDR 2000 and RDR 2100 can compensate for the angle using the roll trim capability. You can adjust the roll trim with a small screwdriver through access in the radar indicator controller. Once you have the screwdriver in the roll trim access port, slowly rotate it until you achieve an image similar to this, with the inner ring of the graphic display parallel to the range marks on the display indicator. As you observe weather targets on the radar display, you see them in their broadest dimensions. The higher the rainfall rate contained within a storm, the greater its ability to reflect maximum radar energy. When the aircraft's radar is in the weather mode, it is calibrated to display different rainfall rates in the following colors. Black, very light or no rain. Green is 0.04 to 0.17 inches per hour, which is light rainfall. Yellow is 0.17 to 0.5 inches per hour, or medium rainfall. Red is 0.5 to 2 inches per hour, very heavy rainfall. And magenta is greater than 2 inches per hour, or intense rainfall. Pilots flying the RDR 2100 may also see blue areas displayed on their indicators. When selected, the RDR 2100 features automatic range limiting, or ARL circuitry, which allows the system to graphically display areas that the radar cannot penetrate due to signal attenuation. Typically, the RDR 2100 will display blue areas on the far side of a series of severe weather systems. Pilots should avoid flying into these blue areas. Weather cells, which are very active, in particular thunderstorms, contain high levels of turbulence along with excessive amounts of precipitation in the form of rain and/or hail. Flight crews can use the following visual clues to help identify these storm types and access their hazard potential to better plan their evasive maneuvers. A rainfall rate anywhere within a cell displayed as magenta or red. The amount of danger a storm represents to an aircraft is strongly related to the rainfall rate within the storm. A storm which contains areas of magenta or red displays should always be considered a significant threat to the aircraft's safety and must be avoided. The existence of steep rainfall gradients. A steep rainfall gradient is defined as a rapid change in the rate of rainfall within the storm. A steep rainfall gradient is indicated when the distance between no rain and a red area is 2 miles or less. That condition indicates a highly active and dangerous storm. Anytime a steep rainfall gradient is observed, that storm should be avoided by a considerable margin. The rule of thumb is, the steeper the gradient, the greater will be the storm's associated turbulence. The shape of the weather cell. There are some distinctive storm shapes which are well known to represent dangerous storms. They are protruding fingers, scalloped edges, U-shapes, hooks, sometimes associated with tornadoes, and thunderstorms developing in a line. Visual cues that can alert pilots to severe convective weather conditions are a storm moving in excess of 10 knots, a visible anvil shape at altitude, and frequent lightning. It's a good rule of thumb to avoid any storms with these characteristics by at least 20 nautical miles if possible. As a pulse of radar energy travels through a rainstorm, each raindrop scatters a small fraction of the pulse's energy. The more raindrops within the rainstorm, the more of the pulse's energy is lost to this phenomenon. An intense rainstorm will disperse all the available pulse energy within a very short distance, as little as a couple of miles. Once this occurs, the radar's ability to detect targets beyond that range is completely exhausted. This energy loss phenomenon is referred to as a radar attenuation. Any targets that are in the path of the radar pulse but are not illuminated by the pulse because of radar attenuation are described as being in a radar shadow. Another cause of radar beam attenuation that crews should be alert to is attenuation resulting from a heavy sheet of water or the formation of an ice layer on the radome. These conditions will reduce system range performance and cause target intensities to be understated on the radar's display. The RDR 2000 and RDR 2100 can be configured at the time of installation to feature the target alert display. The purpose of this feature is to alert the flight crew to the presence of a significant, red-level, weather cell that exists beyond the currently selected display range. When a target alert is issued, two red arcs separated by a black arc will be displayed at the top of the display centered on the aircraft heading. Should you see this image, select a range further out from the present range to confirm the location of the significant weather pattern. The vertical profile feature of the RDR 2000-2100 provides a direct means of displaying the vertical characteristics of the weather cell. Storm characteristics of particular interest to the pilot include relative height, slant, range shape, vertical development, and the area of most concentrated precipitation within the storm. In addition to providing information about the storm's vertical characteristics, the pilot can now easily distinguish between ground or sea returns and actual weather. Operation of the vertical profile is easy. Press and hold either the TRK track left or TRK right button. A yellow line will appear on the screen and start to slew in the direction selected. Displayed in the upper left corner is a yellow numeric annunciation, displaying the number of degrees left or right of the aircraft nose the track line is positioned. To stop the track line at a desired position, release the track button. Once the desired azimuth is selected with the TRK button, press the VP button to enter the vertical profile mode of operation. When VP is selected, the vertical profile screen will appear on the indicator and the radar will provide a vertical scan of plus or minus 30 degrees at the location of the horizontal track line. See the normal ground returns on the 40 nautical mile range. The center of this image is ground. As the beam is scanned over the ground, the solid returns create a mirror image about and below the ground level, providing reflectivity equal to the beam width and the power level. Displayed as strong, symmetrical ground returns at 130 nautical miles are flat terrain with Denver and the background mountains. When the beam shows a symmetrical image about the ground return center line, either the returns are from a very solid object, such as the ground, or a very intense low-level close-in storm. Watch for non-symmetrical returns. They indicate weather. An intense high-level storm is depicted by the non-symmetrical returns. When 40 nautical mile range is selected, normal ground returns appear out to 25 nautical miles. At 20 nautical miles, the radar shows an area of isolated precipitation between the aircraft and the major storm, which starts at 25 nautical miles. The roll cloud is a fairly typical phenomenon associated with severe weather. Aircraft is on the ground at Fort Collins, Loveland, Colorado. Selecting 20 nautical miles. A shaft of precipitation approximately 3 nautical miles wide starts at 9 nautical miles, rises, and mushrooms. An interesting point between the azimuth and VP presentation is the storm depth painted. The selected tilt angle would account for this discrepancy. The vertical scan in the vertical profile mode of operation is up and down 30 degrees. Normal azimuth scan tilt adjustment is up and down 15 degrees, which limits the upward scan and ability to paint the higher level development of the storm as depicted in vertical profile presentation. Sometimes it's difficult to distinguish ground returns and weather. By placing the track line over the area in question, vertical profile distinguishes between the two. On the left is the vertical profile view of a city, ocean, and storm. On the right is the same storm in standard azimuth view. A vertical profile operational advisory. The RDR 2000-2100 is a weather analysis and avoidance tool. It should never be used for pre-planned penetration of storms. However, in the event of required navigation in areas of bad weather, the proper use of this tool can reduce the likelihood of encountering excessive precipitation and turbulence. The RDR 2000-2100 radar greatly simplifies the task of determining vertical characteristics of a storm by pictorially displaying a vertical slice of the cell and showing its radar height. The accuracy of radar height is limited by beam illumination and range resolution. Since cloud tops composed of ice crystals or dry hail, both of which have low radar reflectivity, or storm-associated turbulence without precipitation, may extend several thousand feet or higher, appropriate caution must be exercised when attempting to overfly a cell which exhibits high radar reflectivity or extends above the flight level. Vertical profile is not intended to measure the absolute height of a storm, although it can be useful in determining relative radar heights of different cells. Flying near or under a thunderstorm should never be attempted, even if radar returns are weak at low levels, due to the possibility of extreme turbulence and wind shear. Lateral clearance of at least 20 nautical miles is recommended for all storm cells, providing red or magenta level returns. Note, the NavMap mode is disabled during vertical profile operation. Also note, vertical profile is most useful in the wing's level operation mode. During a turn, constant adjustment of the track button would be required to view the same area of a given cell. Roll stabilization is not functional during vertical profile operation. Therefore, during a roll, the vertical profile slice angle equals the bank angle of the aircraft, providing a skewed vertical profile display. The primary purpose of weather radar is to identify and avoid dangerous weather before you are in it. To that end, a radar operator must be able to adjust the elevation beam angle of the radar and know exactly where it is pointing. The antenna elevation pointing angle, commonly referred to as the tilt angle, can be manually adjusted 15 degrees above and below the horizontal plane, as was previously described. This capability allows the radar operator to point the beam of the radar at the thunderstorms at various altitudes. Auto tilt on the RDR 2100 allows the antenna position to be automatically adjusted to maintain a common beam intercept point with the Earth. For example, if the last 25% of the screen is ground, then during ascent or descent, the tilt is automatically changed to maintain 25% of the screen returning ground. Before describing some useful techniques for both tilt and range management, it's necessary to briefly explain the reflection characteristics of thunderstorms. Thunderstorms come in two forms, frontal and air mass. Regardless of their type, they have a typical radar reflection profile. The lower part of the storm, the section below the cloud base, is composed entirely of raindrops and is a good radar reflector. The section between the cloud base and about 18,000 feet also contains raindrops and is a good radar reflector. Above that altitude, the precipitation is frozen and is a poor radar reflector. In order to produce an accurate radar return from the rainstorm, the beam of the radar needs to be directed toward the lower 18,000 feet of the storm. Through tilt management, this goal can be achieved. Let's say the radar is being used on the 80 nautical mile range, in the weather mode, while at an altitude of 30,000 feet AGL. The goal is to keep the display relatively clear of ground returns while making certain that no weather cells go undetected in or near the aircraft's flight path. One of the most difficult tasks when using airborne weather radar is separating weather targets from ground targets. This is especially true since the maximum return from a storm cell occurs when the radiation beam is centered on the rainfall shaft. In many cases, this shaft may be no higher than 5,000 feet, thus requiring some antenna down tilt to observe it. If you are flying at an altitude considerably above this, the antenna beam will also strike the ground, masking the storm cells with ground targets. In these situations, the proper adjustment of the antenna tilt will help you achieve optimum target identification. Start by using the tilt control to point the antenna down, so that the ground return stripe can easily be identified. A tilt angle of -10 degrees should be adequate. The absolute value of the down tilt angle is of little importance. The key element in this procedure is to place the ground return stripe at a location where it can be easily identified by the radar operator. At -10 degrees, the center of the ground stripe will be located at approximately 30 nautical miles. At this point, you can think of the radar's beam as illuminating the Earth's surface in a manner similar to the way a searchlight, mounted on the front of the airplane and pointed at a similar angle, would illuminate the ground in front of it. Now, slowly increase the tilt angle to lift the beam. As the beam is lifted, you will be able to see the ground stripe reflection moving further out in range. Weather radars typically scan from one side to the other side in about 4 seconds, so be patient and make the tilt adjustment slowly. Continue to move the beam outward until only the outer edge of the display range contains ground returns, let's say about 5% of the display. Raise the antenna tilt angle until the weather is separated from the ground. Note that the displayed range of the ground target will increase as the tilt angle is increased. Also be aware that the intensity of the echo will appear to weaken because the radar is now looking at the upper section of the cell, where most of the precipitation is in the form of hail or ice, which are both poor reflectors of the radar signals. Because of this, it is mandatory that the beam be pointed at the wet part of the weather cell to detect the maximum rainfall intensity, the color level. To aid the pilot in accomplishing this task, the radar tilt angle calculator is provided. This tool is a transparent 3 dB beam width overlay for each antenna size and range scales of 40, 80, and 160 nautical miles in length, each of which has multiple weather cells shown to scale at different distances. A user can position the overlay on a given target and read the tilt angle that will position the beam at the above freezing part of the cell. If there is still a question as to whether the echo is a weather or ground target, the vertical profile mode should be selected. That's it. That's all that is necessary to adjust the radar for proper tilt management on any display range. Now, as the aircraft moves forward, if rainstorms move within the displayed range, their highly reflective bottom section will encroach into the beam's path and be presented on the display unit. As you fly toward a storm, its display will move forward of the ground returns, creating an easily identifiable shadowed area behind it. At high altitudes, over 25,000 feet, as you fly closer to the storms, depending on their intensity, their display presentation may change colors or disappear entirely from your display because the beam is overscanning the most reflective part of the storm. As your flight progresses along its route, you might want to keep track of a storm that your system has begun to overscan. To do this, you simply reduce the display range setting and repeat the previous procedure. With a little practice, you'll be able to set up a display range very quickly. Letting the radar beam overscan a storm which is off to the side of your flight path is okay. It is, however, ill-advised to fly through the clear air above a storm cell or penetrate the less reflective storm top. That area of the storm can be very dangerous due to the unstable air and the possible presence of hail. Overscanning by setting the tilt too high is undoubtedly the most common mistake pilots make when operating a radar. If you change altitude, consider the geometry of the scenario. If you descend, you need more up tilt to display the correct radar picture. And if you ascend, you need more down tilt. You should adjust your antenna tilt each time you significantly change your flight altitude. Coupled with the requirement for good tilt management skills is a requirement for good range management skills. Range management means to choose the radar display range that is proper for your flight altitude. If your flight path is below 18,000 feet AGL and you use the recommended tilt management procedure, you can use any display range and not be in danger of overflying a dangerous storm. In that case, simply select a range which will give you adequate warning time so that you can make an avoidance maneuver in a timely manner. At the higher altitudes, it is important to remember that you are flying above the most reflective part of the storms, and consequently, you will require a significant down tilt to make certain no storm goes undetected. If you ever find yourself in doubt about whether or not the tilt position is correct after you have made a range change, move the tilt angle down briefly and readjust the beam to give the correct amount of ground return. The best way to develop good tilt and range management skills is to practice them in good weather. Once you have gained these skills and refined them, it will be a simple matter to properly adjust the tilt and range controls for safe weather avoidance. At long distances, as was previously described, the energy within the pulse spreads out over a large area. At 100 nautical miles, the beam is 30,000 feet in diameter. That means that at least half of the pulse energy is going to overshoot the most reflective part of the storm. A secondary effect is that at long viewing distances, the Earth's surface starts to block targets which are beyond about 150 nautical miles. The combined effect of these two factors make detecting rainstorms at long distances more difficult. If rainstorms are detected at long ranges, say over 100 miles, regardless of their displayed intensity, consider them significant storms and make course deviations as early as possible. Ground mapping refers to the process of using the Earth's surface as a radar target. The radar will ground map in either the weather mode or the map mode. The main difference between the two modes is the way the radar processes echoes. To use the radar in ground mapping mode, first press the Ground Map button. Then adjust the antenna tilt control downward until the terrain appears. Ground map colors are green for weak returns, yellow for moderate returns, and magenta for intense returns. The map symbol will also be displayed in the lower left corner of the PPI. The larger the downward antenna tilt angle, the closer the detected terrain will be to the aircraft, and the smaller will be the illuminated ground area. This reduction of the illuminated area is due to beam width effect. The radar beam width in the map mode is 8 degrees wide for a 12-inch antenna. The same as in the weather mode. Like precipitation targets, terrain targets exhibit different reflectivity qualities. It is this difference in reflectivity that produces a unique map. The display will provide a map view of prominent landmarks such as cities, lakes, rivers, shorelines, and other terrain features that lie within the beam of the radar. Because the intensity of ground returns vary widely due to the changing angles that the radar's beam is illuminating objects on the ground, the flight crew may use the manual gain control to obtain an interpretable ground mapping display. A good rule of thumb is to fine-tune a map display by varying both the gain and antenna tilt controls until the presentation is optimized. The gain control knob is active in ground map mode for both radars. The RDR 2100 is configured at installation time to be enabled or disabled in the weather mode. Warning: pilots need to be aware of their aircraft's system configuration, because the gain control reduces the sensitivity of the radar unless it is turned fully clockwise. Whenever possible, it's good practice to sharpen your mapping skills on known ground targets in good visibility. When attempting to map sea returns, be aware that calm water provides a very low radar reflection. It acts like a mirror and reflects the pulses forward and away from the receiver. The same is true when viewing the sea from a direction parallel to the waves. A much stronger reflection can be observed when viewing the sea in the up and down wind directions, the upwind being the strongest. Sometimes a city may be mistaken for a weather cell while operating in either the map or the weather mode. This can happen because a city has the same general appearance on a radar display as does a storm cell. It has a red core area, which is downtown. It has a yellow outer skirt, the suburbs, before it tapers off green and broken black, the outskirts of town. If you learn to look for a radar shadow, however, you can always differentiate between a storm and a city. That is because the city does not extend into the sky very far and therefore does not cast an appreciable radar shadow. Another interesting ground target is a mountain. It has a crescent shape and a shadow behind it. It is slightly more difficult to identify as being a ground target than a city. Mount Hood, Mount Rainier, and Mount Shasta, near the Pacific coast of the United States, are good examples of mountains that are fairly isolated and look like isolated, intense storms. Be very careful to know where they are located. Some useful weather evaluation and avoidance techniques. If you adjust the radar beam angle to remove all ground returns from the display while maintaining a strong reflection from the weather cells, the weather display will appear as shown. You can see that the most intense part of the storm is hidden from view and dangerously understated. If you did not identify the crescent shape on the front edge of the storm cell and realize that a significant radar shadow is present, you might make the decision to fly toward the area which appears clear, an area that is, in fact, the most dangerous part of the storm. A proper technique which will allow you to effectively evaluate the weather conditions in this scenario is to adjust the tilt so that the radar's beam is directed toward the ground. This procedure allows you to identify the radar shadow which is being cast by the dangerous thunderstorm and take precautionary measures to avoid that storm. Extended areas of rainy weather sometimes contain embedded thunderstorms. If an aircraft is flying in this type of weather, its radar beam will be significantly attenuated by the extended intervening rain. This will reduce its overall range performance. If the beam of the radar is adjusted to only display rain echoes, the display will appear like this. As the aircraft approaches the embedded thunderstorm, the display will change to this. Seeing this presentation, you might not realize that the crescent shape of the outer edge of the weather pattern is the result of a thunderstorm attenuating the signal and creating a radar shadow. If you mistakenly interpret that area as a clear zone, you will probably make the wrong decision to fly toward it. If, on the other hand, you adjust the radar tilt to direct the beam toward the ground, you will see this radar presentation. Now, when you approach the embedded thunderstorm, you will see the ground returns become shadowed and immediately make the decision to fly away from that area. Under these weather conditions, always fly toward the displayed ground returns. Although the procedure described works well in extended rainy conditions, we cannot overemphasize that weather radar should be used for weather avoidance, not penetration. The weather radar industry uses the term spokes to represent any presentation on the radar display unit which resembles wagon wheel spokes. The main cause of spokes is usually interference from powerful military ground radar. This does not indicate a radar system failure. If you are uncertain whether the radar system is malfunctioning or if the spoke is being caused by an external source, change the heading of the aircraft slightly and notice if the heading of the spoke changes in the opposite direction the same number of degrees. If it does, it is external interference. Ignore it. A set of suggested guidelines for using a weather radar throughout a typical flight, as found in the pilot's handbook. While the aircraft is parked at the gate and taxiing in congested areas, keep the radar system in the test mode. Note, when the knob is switched directly from off to on mode, the display will blank. As the radar sweeps, the blue-white pattern will grow outward. This progression allows pilots to gauge the status of the 60-second warm-up period. Just before this warm-up period is complete, the screen will turn black for a few seconds. Then the radar will begin transmitting and the screen will display radar returns. No radar transmissions occur until the warm-up period is complete. Once the aircraft is clear of personnel and fuel trucks, set the mode control to the weather mode and the range control to 10 nautical miles. Adjust the antenna tilt control to display ground returns as a confidence check. This procedure ensures that components not checked previously in the test mode are working properly. With the aircraft pointed so that the antenna can scan the intended departure area, slowly rotate the antenna tilt control to +9 degrees while looking for convective weather. If the 10 nautical mile range is clear, repeat the operation for the 20 and 40 nautical mile ranges. Look for dangerous storm shapes while being particularly sensitive to crescent-shaped storms. Remember, crescent-shaped storms are likely to be hiding dangerous weather. If your evaluation of the takeoff area indicates a safe zone, leave the range set to 40 nautical miles and adjust the tilt control to +4 degrees for takeoff and initial climb out. A special note: on aircraft that use conventional gyros, set the tilt to +7 degrees instead of +4 degrees. This additional +3 degrees compensates for the 3-degree acceleration error caused by precession of the gyro during acceleration. Precession error affects both pitch and roll during takeoff and climb out. For aircraft with conventional gyros, the acceleration error will continue until the aircraft reaches a steady-state airspeed. Once the aircraft is in a steady climb, it will take approximately 3 minutes for the vertical gyro to stabilize and provide the radar with a correct attitude reference. As a rule of thumb, on climb out, pilots should reduce the initial tilt setting by approximately 1 degree for each 10,000 feet of climb, or until ground returns appear on the outer edges of the scope. Once the ground returns are presented on the outer edge, small adjustments to the tilt can be made to maintain that presentation. Around 20,000 feet, switch to the 80 nautical mile display range and set the antenna tilt control to 10 degrees down. Slowly rotate the antenna tilt control up while watching for weather cells, until ground is being only lightly painted on the outer edge of the displayed range. As the climb proceeds, continue to make small adjustments to the tilt as necessary, until the aircraft reaches the cruise altitude. This procedure will correctly point the antenna beam and create a zone where no storms can go undetected by the radar. Some pilots prefer to use the 160 nautical mile range at cruise altitude. If that is your preference, switch the radar to that range and repeat the tilt management procedure. If during the flight a radar system is suspected of having poor range performance, a confidence test should be initiated. A radar system that is functioning correctly should display ground returns out to a distance of at least 120 nautical miles. To perform this test, the aircraft needs to be at an altitude of at least 21,000 feet AGL. Rest assured that if the radar will display the ground returns at that distance, it will certainly display the weather correctly. Whenever an en route storm is being evaluated, aggressive use of down tilt is necessary to direct the beam into the lower 18,000 feet of the storm. A subtle form of overscanning can result if a low-altitude thunderstorm is rapidly building. Some convective storms grow at rates of up to 8,000 feet per minute and can rise up under your flight path as you approach them. If convective activity is high in your area of flight, it is a good idea to lower the beam from time to time to look for rapidly developing storms. A blind alley, or box canyon situation, can be a dangerous trap for pilots that habitually fly with the radar on a short range of 40 nautical miles or less. The short-range returns show a corridor between two areas of heavy rainfall. The long-range setting shows the trap. Always switch to the long range before entering such a tempting corridor. When flying over water, where you cannot always be guaranteed an adequate ground reflection, the following tilt settings are suggested. At a range of 40 nautical miles, 6 or 7 degrees down. At 80 nautical miles, 3 to 4 degrees down. At 160 nautical miles, 2 to 3 degrees down. En route deviations should always be made upwind of a storm. Deviating downwind increases the chance of encountering hail and turbulence. You can expect turbulence 1 nautical mile downwind for each knot of wind speed at your altitude. As a general rule, you should avoid thunderstorms by the margins shown. 20 nautical miles above 20,000 feet, 10 to 15 nautical miles, 10 to 20,000 feet, 5 nautical miles below 10,000 feet, and 3 nautical miles in the terminal area. On descent, in order to maintain the proper display presentation, it will be necessary to adjust the tilt up approximately 1 degree for each 10,000 feet of reduced altitude. Weather evaluation of the terminal area should begin at about 70 miles out. This evaluation should include aggressive use of the tilt control to assess the intensity of any weather targets in the area. If a storm is located in or around the terminal area, adjust the radar's display range to emphasize the storm's location, and adjust the tilt control to direct the radar beam toward the bottom of the storm. By following this procedure, you'll be able to observe if any radar shadow exists. If one does, fly away from it. Again, if there is any question as to whether the Echo is a weather or ground target, the vertical profile mode should be selected. On final approach, adjust tilt to 6 degrees up using the 10 or 20 nautical mile range. This will allow the radar beam to safely scan the terminal area for weather activity, while eliminating ground returns and minimizing the radar workload. Evaluating weather should be an ongoing process until the landing is completed. Keep the radar display in your view and be prepared to initiate a go-around if threatening weather appears on the scope. This video has covered the following subjects: a basic understanding of radar operation, a description of how to use weather radar to detect and avoid dangerous weather cells, a set of suggested guidelines for using a weather radar throughout a typical flight. As a general comment, it should be noted that the most important radar skill a pilot can possess is the ability to use the ground echoes as a reference point for proper tilt management. By learning to use the beam to observe the ground in good weather as often as possible, you will become familiar with its reflection characteristics. Having gained this familiarity, you'll be able to properly adjust the tilt angle of the antenna to make valid assessments of the weather conditions. Remember, weather radar is a vision extending tool for pilots that provides significant warning of hazardous weather. Use this tool wisely, and it will add to the safety of your flight.